That was nice, thanks. Hey everybody, thank you so much for coming. Like you said, today I'm going to be presenting on behalf of Goliath Resources from my master's research titled Geology and Genesis of the Golddigger Property, British Columbia. So we're going to start off just with the geological context. This is a map of British Columbia. These are all the terrains. The largest one right here is the Stikine Island Arc terrain. It was a long-lived Mesozoic island arc that was accreted in the Cretaceous. I'm introducing this because the Stikine Island Arc plays a large role in exploration in British Columbia and the Golden Triangle, which I'm going to touch on right now. So the Golden Triangle is an area in the mid-central western British Columbia here, and it is known for prolific gold past producers, explorations, and current producers. So there's some real all-stars on here. Just to name a few, we have Galore Creek, KSM, SK Creek, down here to the south, Porter, Idaho, and of course, Goliath's Golddigger Sherbet property. So an important thing to emphasize here is a lot of the deposits, past producers and current producers and prospects are thought to be related to Stikine arc magmatism. So related to back when this terrain was an island arc before it was accreted onto the continent. So Golddigger down here, when it was first discovered, it was thought to be exactly the same. If you get a bit more zoomed in, this is the Stikine Island Arc terrain right here. It's on the western fold right here. So Golddigger is about 10 kilometers southwest of Dolly Varden here, and then 25 kilometers northwest of the Kitsault molybdenum porphyry. So I'm going to show you some rocks in a second, but just so you know, the mineralization here consists of polymetallic quartz sulfide veins enriched in electrum, which are cutting the Upper Hazelton volcanic rocks, Upper Hazelton sedimentary rocks, and Bowser Lake group sedimentary rocks. So since its discovery, the deposit model and age for Golddigger was sort of debated and controversial, so that's kind of why I'm here. So here are the modeled mineralized zones as of about 6 months ago. This is what I was basing my research off of. We have several zones here. The ones that I focus the most on are the Sherbet and the Bonanza zones here. Bonanza exists at the contact between the Upper Hazelton volcanics and the sedimentary rocks, whereas Sherbet exists in a thrust cutting the Upper Hazelton sedimentary rocks and Bowser Lake group rocks. So there are other zones here included, including Golden Gate, Whopper, Eldorado, and my favorite, Goldzilla, but not really focusing much on those today. So here's a cross-section of the Sherbet and Bonanza zones. As you can see, Sherbet's cutting through right here, these folded sedimentary rocks, and then this is, it exists at and near the contact between the volcanic and the sedimentary rocks. Important to note, there are granodiorite dikes right here that cut vertically through the property. They are locally mineralized, hosting high-grade gold, commonly exceeding 10 grams per ton. The gold there is occurring in sheeted quartz veins with bismuth and bismuth tellurides, where these veins outside in the volcanic and sedimentary rocks, those are those polymetallic veins that I'm going to show you right now. So this is a good representative photo of what I have of Sherbet. It's these quartz veins that are cut by late sulfides. The sulfides are dominantly pyrrhotite, and it includes galena and sphalerite as well, local silver sulfur salts, native silver, and of course gold. There are local massive and semi-massive lenses inside of the Sherbet zone. And then Bonanza has similar mineralogy with the pyrrhotite, sphalerite, galena, less local massive sulfides, but the grade is generally a little bit higher. Here are those granitoid dikes I was talking about. They're generally quartz monzonite, they're ilmenite series, and they do host local sheeted quartz veins, which are generally very sulfide poor, but they do occur with bismuth minerals and of course gold. Finally, there's skarn mineralization that's found particularly in the volcanic rocks, although there are some limestone lenses that host it as well. And these, the garnet skarn is found to predate the quartz veining and sulfide mineralization and gold mineralization, so you can kind of see right there how it's being cut. So the research goals, why am I here basically? Well, we want to understand the processes responsible for mineralization at Golddigger. To understand the system is to aid in targeting and to find more favorable lithologies and structures, so having this understanding is very important. Really a highlight was to constrain the timing of mineralization. There's a lot going on in the Golden Triangle. There's a lot of different ages to the lithologies and the structures, so understanding exactly what is favorable for gold mineralization is important. And really, from the get-go, we wanted to focus on providing tangible value to Goliath, not just some abstract stuff, but really stuff that can aid in targeting. So the methods that I'm going to cover in this presentation, though not all of the ones that I used, include just petrography, fluid inclusion studies, CL work, SEM EDS for microanalytical stuff, electron microprobe to understand the chemistry of gold, and finally a whole lot of geochronology to tie it all together. So I'm going to start off by talking about our fluid inclusion study, but I'm going to kind of get you warmed up because I don't want to go too high level too fast. An important part of our story is the post-entrapment modification of fluid inclusions. I know that's a mouthful, but I'm going to put it in English, I promise. So when you form a vein, of course you're going to have fluid inclusions. Those are representative sometimes of the fluids that actually made the vein. But pressure fluctuations will modify those fluid inclusions in ways that record the pressure history of a given sample. So, for instance, right here demonstrated by this figure, if you start a fluid inclusion and you form it under lithostatic conditions, we'll say under the ductile regime, and then you bring it to hydrostatic conditions, or the brittle regime, you're actually going to have such high pressures in this fluid inclusions that once it's brought to the lower pressure hydrostatic realm, it's going to explode. There's too much pressure in there, so it's going to modify the fluid inclusion. Similarly, if you form a fluid inclusion under hydrostatic conditions and then you overpressure it and you bring it under the lithostatic conditions, you're going to buckle the fluid inclusion and you modify it. So this is establishing that by crossing the brittle ductile transition, you're actually going to record that pressure change in the fluid inclusions. This is well established, and it's going to play a role, which I'm going to get into right now. So what we find is that there are two generations of quartz present at Golddigger. The first is the most volumetrically dominant. We call it Q1, very creative, I know. And that quartz is extensively recrystallized, it's locally deformed, and it's hosting several dominantly post-entrapment modified fluid inclusions. So like I was just saying, this stuff, it's buckled and it's exploded and it's very ratty. This quartz has been through a lot. Like I said, it's recrystallized. And it's really in contrast to Q2, which is the later quartz, which forms euhedral and subhedral overgrowths onto Q1. And it never hosts post-entrapment modified fluid inclusions. So we never see evidence of these pressure fluctuations inside of the fluid inclusions. So it's distinct in that way, that it formed hydrostatically and then stayed hydrostatically. And it's not recrystallized nearly to the same degree as Q1. And both of these generations of quartz are predating sulfide and gold mineralization. So we understand that the system starts out as quartz veins with potassic alteration, and then later it switches to hydrostatic with Q2, and it stays that way through sulfide and then gold mineralization that postdates it. So here's a good figure that's demonstrating the postdating nature of the sulfides. It's going along grain boundaries, it's cutting through right here. And yeah, it's just generally scalloping the edges of these quartz crystals. And it also demonstrates pretty well the difference between these generations. As you can see, pretty ratty beat up Q1, and then euhedral to subhedral Q2. When we switch to CL, we can see the difference in the response between these two generations of quartz, where Q1 has a really mottled, patchy response, where Q2 has a more even response. And you can see in there, there's actually quartz growth zones. So that's important because along growth zones, that's where you can find primary fluid inclusions. And those are very valuable to understanding the evolution of a hydrothermal system. So you can see this box right here. That's along a growth zone in quartz. That's this image right here. What we find is that these primary fluid inclusions that were entrapped as the quartz crystal was growing, they homogenize at 350 degrees Celsius. So relatively hot. It's occurring along this growth zone, and you can see it's associated with some arsenopyrite. So we're getting homogenization occurring at 350 degrees C. Another important thing to note about these primary fluid inclusions is they're very rich in CO2. So what we're seeing here is what's called a CO2 double bubble. That is what happens when you have a single phase fluid that gets entrapped that's really rich in CO2. So right here, we have that single phase fluid, we have water right there, we have vapor CO2 in the middle, and then a meniscus of liquid CO2. So this is under a lot of pressure, and it hosts at least 7 to 10 mole percent CO2. So very high, way higher proportion of CO2 than you'd expect in like a porphyry or an epithermal, and that's just due to the pressure that had to have been entrapped at. So given that we know that the high CO2 content is about 7 to 10%, and we know these fluid inclusions homogenized at 350 degrees, we can actually use this model to determine that for a fluid to exist at that temperature, it needs to be at about at least 500 to 600 bar. So how deep that is in the paleo, what's the paleo depth of that depends on whether or not you're hydrostatic or lithostatic, right? Well, we've already established that we're in the hydrostatic realm because we haven't experienced those pressure fluctuations. So knowing that we're hydrostatic, 500 to 600 bar, that's about 5 to 6 kilometers. So that's tremendously deep relative to, say, an epithermal or a porphyry. So this tells us a lot about the setting that we're in, and really that excludes a lot of different deposit models. It leaves you with orogenic or intrusion-related. So, but I'm getting ahead of myself. So we have two phases of gold that we find in our petrography. So all of this is post-dated in Quartz. As you see here, here's an intergrowth between bismuth telluride, it's a headlayite, and then gold. This is the earliest assemblage that we find. It's associated with higher temperature alteration minerals like scapolite and actinolite. And what we're finding is, these two are very commonly found together in a higher temperature, earlier assemblage. And it's post-dated by, right here, a late stage of gold that's associated with chlorite, which comes through and replaces earlier alteration. It's not found as composite grains with bismuth. It really does occur on its own, and it's generally more silver rich. So we did the most of the microscope study on the late stage of gold, which I'll get to in a minute. As for that chlorite overprint, it is clearly a later, cooler stage that's overprinting earlier minerals. So right here we have chlorite, which is fanning out along and replacing biotite alteration here. And then here is chlorite veinlets cutting through actinolite and replacing the actinolite. And as you can see here, the gold, everywhere you have the gold in here, it is associated with the chlorite alteration. So that sort of backs up the reflected light image I was just showing you. As for the precious metal geochemistry, we use microprobe on those late assemblages of gold. And what we find is that the chemistry of this gold actually clusters depending on where we're at in the system. There's a spatial zonation that you see. So the highest fineness gold clusters, this red assemblage clusters, green, yellow. These are all different locations, which I'll show you on a cross-section in just a minute. And then this is native silver. We also find that the amount of antimony is increasing as the silver grade increases. Furthermore, we find that the mobile elements are actually strongly correlated to the silver grade, which the silver grade is, I'll show you right here, increasing up the structure. So this is the volcanics down here, remember, this is the sedimentary rocks that have been folded and thrusted. And as you see up here at the top, that is where the electrum is the lowest fineness. It's 30 weight percent silver, or 30 weight percent gold, 66 weight percent silver, and then a whopping 3.3% antimony. And as you go down the structure, it's getting more gold rich. We still have antimony above detection limit here. And then down here in the volcanic rocks, so that's where we get the highest fineness in our electrum, and the lowest proportion of silver. So there's actually a geochemical gradient pointing us up the structure, saying that we're concentrating mobile elements up here and less mobile elements down here. Now for the geochronology, this was the exciting part, well, at least the most exciting part to me. The weighted average for our garnets, which remember, those are our earliest alteration minerals. You can see right here, these euhedral garnets are being cut by sulfides, just in case you didn't believe me. These truly predate the sulfides. And we get a weighted average from 3 samples for uranium-lead dating of 52.2 plus or minus 1.6 million years. That's not Mesozoic, that's Eocene. But, you know, it's one date, so we have to tie it together, right? Well, we have those gold mineralized dikes I was telling you about as well. We have uranium-lead dates for those, and that gives us 52.0 plus or minus 1.5 million years. So it converges very well with our garnets, but that's not all. The fine folks at Airy and Fort Collins have dated our molybdenite, which are associated with our sulfides, and we find that those are 52.14 plus or minus 1 million years. So we have 3 different methods of geochronology all converging on about 52 million years, so a firm Eocene date. This is especially relevant given that the Hydropluton is less than a kilometer to the west of mineralization, and that is about 52 million years as well, and we know our veins are cross-cutting the metamorphic oriole of the Hydropluton. So it's not Mesozoic, it's in fact Eocene. So to synthesize all that together, there's strong evidence suggesting that Golddigger is an intrusion-related system. Starting with our fluid inclusion evidence, we know this is a very deep setting, deeper than a porphyry or an epithermal, so then it's up to discerning between orogenic or intrusion-related, but we have strong presence of geochemical gradients, we have high to low temperature overprinting of alteration minerals, we have semi-massive to massive sulfides, including base metal enrichment. So that is very typical of an intrusion-related vein and much less typical of something else. Furthermore, the coincident age with the hydropluton is cause for suspicion, as well as the local Kitsault molybdenum porphyry, which is dated at 54 million years. So it's not the first example of mineralization related to this magmatic influx in the Eocene, but it is the first intrusion-related gold and the first Eocene gold mineralization noted in the entirety of the Golden Triangle. Finally, the association between bismuth minerals and gold inside of intrusions that are coincident with the rest of the geochronology is typical of an intrusion-related system. So the implications for this, like I said, this is the first Eocene intrusion-related gold in the Golden Triangle. That has implications for a few reasons. First, this sort of system hasn't really been described in the Golden Triangle by any means, and the conventional wisdom is that all the gold here is Mesozoic. It's related to the Stikine Island. Well, this postdates accretion by 40 million years. It's related to a magmatic influx that happens in the Eocene. And that is not established by any means, that these late intrusive units are related to gold. But we plainly see it here. So, for instance, the Coast-Plutonic complex, which hosts the hydropluton, has been systematically ignored for gold exploration. In fact, after these studies were done, we had the data. Goliath picked up increased its land package by 20%, picking up Coast-Plutonic complex rocks, because clearly we know better now. Furthermore, for exploration on the property, the classification as an intrusion-related vein is important because intrusion-related systems are known to have geochemical gradients, which can point towards a causative intrusion. And these sorts of systems are often hosting mineralization inside of said causative intrusion. So being able to vector towards that has the potential to put real ounces in the ground. Anyways, thank you guys so much. I'm happy to answer some questions.
We do have time for questions.
You have a lot of CO2 in the fluid inclusions, but it also sounds like you have a lot of carbonate nearby to generate that CO2. Is that, in fact, that interpretation, you got scar minerals, I'm hearing a lot of calcium.
Yeah.
You know, so the fact that you got CO2 rich inclusions next to a limestone, was that in a skarn, what does that really tell you?
Well, so two important notes. The skarn that's present is in the volcanic rocks, not in the sedimentary rocks. There are very, very few limestone lenses at the present at the property, only in the Upper Hazelton and Bowser Lake group. So the amount of limestone is pretty small, but you're right, you could produce CO2 with that sort of reaction, but the important part is it would have to be trapped as a single-phase fluid. Reacting with a limestone would make a multi-phase fluid because the carbon dioxide would be admissible to the fluid that's generating the carbon dioxide. To entrap a fluid inclusion with that much CO2, it has to be a single phase as it's entrapped. In order to have a single phase fluid at that entrapment, it has to be 500 to 600 bar. Otherwise, the CO2 is admissible and the two won't be entrapped in the same inclusion.
Great talk, Randall.
Thank you.
You mentioned the Kitsault intrusion at 54 million years?
Yes.
Is that dated down where the Kitsault mine is 25 kilometers south, or do you have Kitsault-like intrusions
Yeah.
in the area of Sherwood?
So that comes from a radium osmium date published last year from the BCGS. They dated it, it's coincident with the potassium argon date that was put out like 40 years ago. But yes, that's from the actual Kitsault mine, which was producing for about 5 years back in the late 70s and early 80s.
The 54 age.
Yeah, the 54 million year
Of course,
age.
you know what I'm thinking, but I'll
Yeah.
leave it there. Okay.
We'll talk.
We'll talk, yeah.
Yeah, are Q1 and Q2 easily distinguished in the field? I mean, textually, orogenic ones versus epithermal?
They're quite hard to distinguish in the field because Q1 and Q1's so dominant and Q2 so rare. It's very apparent when you get to the sulfide-bearing zones because you actually have preserved euhedral quartz crystals that are embayed inside of sulfides, and very rarely you can find open space euhedral quartz crystals. Yeah.
Do you know how that age compares with SNP, another deposit that Geochemical worked on?
Yeah, so
The Eocene.
The date that I've read for SNP, there is a potassium-argon date for the mineralization, which funnily enough did come back Eocene, but that was disregarded because it was postulated that that was an overprinting, that was a resetting of the date. The paper that I read favors a date for the local intrusive suite, which is Mesozoic, but I'd love to date SNP. Yep. Thank you.